Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This lecture is on ARMA modeling, and in this lesson, I will introduce extensions of ARMA models for non-stationary time series. Let's return to the ARMA model. To review, the ARMA model consists of two components, joint AR and MA models. We'll expand this model, we'll extend this model further as I will provide in the next slide. A generalization of the ARMA model is the auto-regressive integrated moving average, or abbreviated ARMA. The ARMA model can be used to model non-stationary processes. The non-stationarity is eliminated by a differencing step corresponding to the integrated part of the model. The differencing can be applied more than once until the resulting time series after differencing is stationary. How can we express this formally? Given a time series xt, we apply the differencing polynomial 1 minus b to the power of d. This additional polynomial applies one lag differencing d times. The resulting process after differencing yt is further modeled using an ARMA process. If the process yt after differencing is a causal process, then xt is said to be an ARMA process of orders p, d, q. If we multiply the AR polynomial phi b with the differencing polynomial 1 minus b to the power of d, we obtain the polynomial phi star of b. Thus, the ARMA model can be written using a similar structure as the ARMA process, except that the phi star b polynomial of ARMA has d zeros on the unit circle. One way to identify whether a process is non-stationary or ARMA is that a ARMA model usually exhibits slow decay in the autocorrelation function. In order to obtain best unbiased linear prediction for an ARMA process, we assume that the ARMA process is a causal process. For an ARMA process, this assumption does not hold, and thus we cannot apply the prediction methodology for ARMA. Importantly, the expectation and the covariance of the ARMA process are not uniquely determined. In order to obtain the best linear predictor for x of xn plus h, given the past observations of the time series, we need to first obtain the best linear predictor for yn plus h of the yt process obtained after differencing. The prediction formula for xn plus h is provided here. It is the difference between the best linear predictor of the yn plus h and the weighted sum of the predictions of the lower lag predictions x and h minus j. Thus, to obtain the prediction in lag h, we need to solve this recursively. For this prediction of the ARMA model, the variance can be estimated approximately as the sum of the squared coefficient psi times the variance of the white noise process zt, where the coefficients psi are derived similarly to the coefficients of a causal process. The ARMA model described so far can be used when there is trend in the time series. The trend can be eliminated through differencing. Another extension to the ARMA model is the seasonal ARMA, which can be used when there is seasonality. In order to model seasonal time series, we use different lags in the AR and MA components. For example, for the seasonal MA process of order capital Q, we do not use ZT minus 1, ZT minus 2 to ZT minus Q lags, but we use ZT minus S, ZT minus 2 times S up to ZT minus Q times S, where S is the period and capital QS is small q. Similarly, for a seasonal AR process, instead of using the lags of xt minus 1, xt minus p, we use the lags xt minus s, xt minus 2 times s, xt minus p times s. Combining this decomposition gives us the seasonal ARMA process. In this slide, I'm providing a more formal representation of the seasonal ARMA process with the specification of the ARMA orders of the stationary process, small p and small q, along with the orders used to model seasonality as the previous slide, capital P and capital Q. To express this in the model equations, we define the 4 polynomials as provided on the on this slide, with the first 2 defining the autoregressive models and the second defining the moving average models. We can now combine the 2 models, ARMA with seasonal ARMA, to obtain the seasonal ARMA. Let's take a closer look with one example. Consider the basic decomposition discussed in a previous lecture. That is, decompose a time series into a trend component MT, seasonality component, and the residual process ZT. Assume further a model for the trend and seasonality where the trend only depends on the previous lag and the period of the seasonality is S. If we apply the differencing 1 minus b for the trend and 1 minus b to the power of s for seasonality, then the residual process is stationary with autocorrelation at lags 1, t minus 1, s and s plus 1, which agrees with the seasonal model ARMA 0, 1 for the stationary component and 0, 1 for the seasonal component with seasonal period s. This is one particular example of a seasonal ARMA. More generally, we can consider 1 minus b to the power of d differencing polynomial for the trend and 1 minus b to the power of s, all to the power of capital D for seasonality. Because there are many orders to determine those of ARMA PDQ along with those of the seasonal ARMA capital P, capital D, capital Q, such a model is difficult to implement. In summary, in this lesson, I introduced 2 extensions of the ARMA model. The ARMA, which is an extension of the ARMA for non-stationarity due to the trend, and the seasonal ARMA, which is an extension for accounting for seasonality. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This lecture is on concepts of ARMA models, and in this lesson, I will conclude this lecture with an example on illustrating ARMA modeling. In this lesson, I'll return to the emergency care data example used to illustrate basic time series modeling. In this example, time series models can be used to forecast future ED patient volume. So far, we estimated the trend and seasonality of this time series and then subtracted those 2 components from the time series to obtain an approximately stationary process to be modeled with ARMA. In this lesson, we'll consider the differencing approach. First, let's consider differencing to account for seasonality. Note that we identify both monthly and day of the week seasonality. To difference for monthly seasonality, we need to instead difference annually, since the ED volume data are recorded daily. For day of the week seasonality, we can difference with frequency equal to 7, which will apply the difference from consecutive Mondays, Tuesdays, and so on. Note that in order to apply the difference R command, I transformed the time series using the TS command with frequency equal to 365.25, indicating that this is daily data. We next compare the time series plots for the original time series versus the difference time series plot along with their ACF plots. These are the time series plots. The first one is for the transform ED volume. The next is for day of the week, differencing And the last is for monthly seasonality, which is in fact an yearly differencing time series. While we see clear periodic patterns in the original time series, those patterns are not evident in the time series plot of the differencing processes. These are the ACF plots for the 3 time series. The upper plots are the ACF and PACF plots for the original time series, whereas the bottom ones are the ACF plots for the differencing processes. The ACF plot of the original time series clearly shows a periodic pattern, while the PACF does not, as expected. The ACF plots for the weekly differencing and for the annual differencing processes show an improvement in terms of removing the seasonality, although there's still some potential seasonality or some other residual source of non-stationarity. Next, I fitted a seasonal ARMA. Because we have both trend and seasonality, we need to fit an ARMA to account for the trend and a seasonal ARMA to account for seasonality. The R command is the same as for the ARMA fit as ARMA, except that now we are fitting multiple orders, both for the ARMA and for the seasonal ARMA. The input order for the ARMA are 5, 1, and 5. Meaning that we have an order of AR order of 5, a differencing order equal to 1, and an MA order equal to 5. We also use a seasonal order of 1, 0, 1, which means that we're fitting a seasonal ARMA with the AR order equal to 1 and MA order equal to 1. Note that one limitation of the seasonal ARMA is that it only can model one type of seasonality. In this data example, we establish both weekly and monthly seasonality, and thus would be more appropriate to fit both types of seasonalities. These are the residual plots. The first one displays the standardized residuals. From this plot, we do not identify a pattern of the residuals with relatively constant variance over time. The upper plot on the right is the ACF plot of the residuals. Note that for this, I specified a large lag to identify any other potential seasonality. The residuals are all small, most of them within the confidence band, an indication that the residuals may be white noise. The bottom plots investigate the assumption of normality, which is assumed in the maximum likelihood fit. The residuals do show skewness, although it's not very severe. Last, let's see how we can forecast with ARMA. For this, I left out 2 weeks of the data, the last two weeks in a time series. Then I fitted the same ARMA model as provided in the previous slide, but this time to the time series without the last 2 weeks of data. Last, I applied the prediction command in R that allows to predict, given the fitted model as input, and given the number of lags ahead to obtain the prediction, in this case 2 weeks. In this example, we compare the predictions for the 2 weeks with the observed time series. We first form the confidence band of the prediction with the upper bound provided by U bound and the lower bound provided by L bound. Then we plot the time series data. We do not plot the entire history of the time series, but only the last 4 weeks of data. We overlay the predicted values in red along with the confidence band in blue. The corresponding plot is here. The black line is the observed time series. The red points are the predicted values along with the confidence band in blue. All the observed values are within the confidence band, and the predicted values are somewhere close to the observed values, except that they do not capture the volatility in the observed time series. In summary, in this lesson, I concluded the lecture on ARMA modeling with an illustrative example of fitting seasonal ARMA. Thank you.